I'm going to do a video here about trinomial and factoring trinomials. And I'm also going to show you something that's kind of interesting with area and trinomials. So if we have a trinomial example here, like x squared plus 9x plus 20, we have to find factors that multiplied together equal the same, basically the same area. If we figure this is area plus this plus this. And I'll show you, you might be like, well, they're not all squared numbers, but imagine that this is area, and then you want to multiply two factors times each other and have them equal the same thing. So basically just factoring a trinomial for right now. You're going to have x and then either plus or minus some term, x plus or minus some term here. To find what these numbers would be, they have to, like if you're not using the quadratic equation, if you're just doing factoring, they have to add up to this number, and when multiplied, they have to equal this number. So if you go through some examples like 1 and 20, or 2 and 10, or 5 and 4, 5 and 4 add up to 9. So if we go plus 5, oops, plus 5 and plus 4, they're going to multiply to 20 and also add to 9. So if we go redo our work, we go x squared because we're multiplying these, and then 4x, that's 4x, and then we go 5 times x, was 5x, and then we go 5 times 4, we get 20. Then we can just take these and put them together, so we end up with x squared plus 9x plus 20, which is what we originally had up here. Same thing. So if we were to look at this as area, I made like a little Excel macro to illustrate a concept that I saw in this book and on this page right here. On page 37, problem 179 and 180. Here's the ISBN number. I thought it was a very interesting concept that helped me think of trinomials, polynomials differently. So if we consider what we're factoring here, x plus 5 and x plus 4, as dimensions to something that create area, like this right here. If we consider these approximately 1 unit across each column and each row approximately 1 unit across, if we pick an x value of 5, for example, and we make these other shapes, since x is 5 here, this is x squared, right? And then each of these is 1 unit across. So this is just 1 unit across, but it's got the same length as x. This is like adding 1x, right? If we have 9 of them, it's the same thing as having 9x. So we have x squared, this right here. Then we have 9x, and then we're adding 20. We're adding like 20 individual units, just one square unit, right? But times 20. These will all accommodate the same area as this rectangle. And this rectangle is x plus 5. It's so 5 plus 10. So that would be, see, the columns are numbered. So if we go like this, and we go 1 through 10, that's the height of this rectangle. And then if we count like how many rows there are, A, B, C, D, E, F, G, H, I, that's the same thing as 10. here. Is it 10? 1, 2, 3, 4, 5, 6, 7, 8, 9. Sorry, that's 9. So that equals this. And I'll show you that after you organize these, there's the x squared. If we take 4 of those 9 and we go in this direction, which is x plus 4 anyway, if you think about it, and then we take 5 of them, we turn them on their sides, we have x plus 5, and then these other 20, they will occupy the same area as what would be left over because there would be a gap here, right? And we have 4 of those by 5 of them. And when we factor, that's one of the reasons, right, that we find 5 times 4, right, is that's the 20. So I think that's pretty cool. Now, looking at other examples, say we have x squared plus 5 minus 6. Let me just go back to this real quick. Actually, I don't think we really need to for this one. So if we just, even if you just look at this, if we break the terms down into coefficients, just into numbers, the first term is x squared, right? So it's just x and not like 2x or 3x. So 1 here, and then this is 5, and this is negative 6. If you take -1 times 6, they're both going to multiply to -6 because one is positive and the other one's negative, and they're multiplying to 6. And when you add them together, one of them's negative, it subtracts. So you end up with 6 minus 1, which is 5. So that satisfies this criterion. And so if you multiply these together, you'd have what we have over here, which is x minus 1 and x plus 6. Again, I have 5 as the arbitrary value for x. It doesn't matter what value it is. So that makes this kind of easy. So 5 minus 4 is 4 of these rectangles across. And then x plus 6 would be the original 5 for x, but then adding another 6 of them, which is what we see. So if we take like one of these, which has the length of x, since that's in this case it's 5, right? We need to add another one, right? So I just turned this one on its side and put it up to these. If you put this rectangle in it, the height at least matches up. But notice that the width in this dimension, the horizontal dimension, does not match up. We still have an extra, let's see, 5 plus 1. That's 6, right? So we have to take away 6 from this for this area to exactly match up. Well, notice in our last term, we have -6, and that's what these are. So if you take these and you subtract away the yellow, like this, oops, it really does add up. So even with subtraction, it still works out. If we pick another example, like this one here, where we have x squared and we have negative x, I'm sorry, and we have -2. We have two negative terms here, and we factor it. So when you think about it, the middle term is negative, and since the second term is also negative, we have to have one of each factor, like a positive and a minus, right? And since the middle term is negative, we know that the larger those two absolute values has to be negative, right? So the -2, because 2 is going to be 1 and 2, right? 2 doesn't have any other factors. So it's going to be x minus 2 and x plus 1. So if we consider this area, this is x minus 2 and x plus 1. And we make the shapes. This is the x squared. and then the middle term was minus 1x. So if we take this here, we subtract, and we fit this over this, the dimensions actually don't exactly match up for this one, but if you take these, they're also minus, and we subtract the area. Notice that this area here is, this is like 3 units on the yellow part, and this is also 3 units. It still equalizes out to the same area. Let's say we have like a more complicated problem with like an actual number in the coefficient, like 3x squared plus 10x plus 8. When we factor it, this is what we get, and this is what's represented by that. This is more difficult to factor though, right? But if we just consider that, if you just take these shapes, right, and you think about how it would fit with a rectangle and how these 8 would fit, um, it might be even easier to do this for some people if you're not going to use the quadratic equation, for example. But also, there's like another way to do this, factored by grouping, which, so we have 3x squared plus 10 plus 8. We can take this 10x and we can break it down into 2 different terms that we could also then just look at as a group with these other terms. So, and this is where you kind of have to decide which terms to use or which way to break up this 10x. But if you consider that we have 3x here and you want to find something to factor with, it might be useful to use, 9, 6, or 3, right? Well, if you take 6, then what's left over is 4. And the 4 works with the 8, right? Because we can factor 4 out of both of these terms, just like we can factor 3x out of these 2 terms when we group them together. When we do that, we have 3x times x plus 2, because 3x squared, we still just have an x left over if we take out the 3x. And here, if we take 3x out, we just have 2, because it's 6x. When we look at this, now what we have are 2 terms added together that have the same thing that they're multiplied times, which is nice because we can just take this outside of parentheses and multiply it times just these 2 purple terms, 3x plus 4, which is what we're doing here. So we've taken something that's also adding descending powers of x here, including just 0x, which is just 1 times 1, which is just 1, and that's times the 8 that we had there. We end up with the same kind of thing, and we just did it a little bit differently. That's actually easier, I think, at least for some of these problems. It was easier than trying to factor it the other way because, well, this problem is a little bit different, obviously because of the coefficient, but like for this one, even that I'm going to show you next, it's like minus 11x plus 2, and it's 15. And that's even not even as a prime number like 3 is. So you have 2 different factors like 3 and 5, and you have to think about the other numbers that you would use. So grouping is kind of useful. And then also just looking at this though, we have the 3x squared, and then you have to figure out how to organize 10x. So 10 of these other green ones. So you can have the 4 this way and the 6 this way. But the 6 this way is actually also a factor 2. So you can actually be expanding this by 2 in this direction for each of these and expanding it by 4 in this direction. And then what you'd have left over is that 8. And those 8 fit nicely in here because it's 2 by 4. And if you take this and put it over it, you can see that the areas match up. And this is x plus 2 and 3x plus 4. Now, moving on to this one, and zooming in on it, you can also use grouping for this. So 15x squared minus 11x plus 2 to 15. So on the next line, we break this up, the 11x minus 11x. If we break it up into 5 and 6, notice that 6 is even, And also, since it's an odd number, though, there are other kinds of ways to do this. But notice that the 5, though, goes into 15 nicely. How many other factors are there of 15? If you think about it, what? 1, 3, 5, and 15. So it's going to be 3 and 5, probably. And so if you pick these two numbers, when you break it down to group it, you can see that this is going to go nicely over here, and this is going to go nicely over here. So when we do that, 15 and 5, we factor out the 5x over here, and we end up with 3x minus 1. And then on this side, we can factor the 2 out of the 6 and the 2. And when we do that, we have negative 3x plus 1. But notice that this is minus 3x plus 1 versus over here is 3x minus 1. So actually, though, on the right side, this is just a negative of that. So all we got to do is take this. Notice we're adding 2 times this quantity. If we take this and we just subtract 2 of this, we can negate this part and have 3x plus 1 inside of here, which is the same as what we have on this side. And when we do that, as we've done here on this line, if you look at it, you can see that these terms are the same and that we have 5x minus 2 that we could do the opposite of distribute out. We can take it out of it and multiply it times the 3x minus 1. So using grouping, that's what we end up with. But looking at the shapes, this is the 15x squared. So we have 15 of these yellows. Notice that it's minus 11x. So we're taking 11 of these things and we're subtracting the area. So we're putting on the inside of the rectangle here. Okay, just imagine that that's exact there. And on the bottom, if we rotate these other ones, we have this one too. These first 4, there's no problem, but this last one, it's going to be redundant, right? Because we already have the full length of these. So you notice that we have this area here, and we have this here. So we can't subtract twice in the same area, right? Well, unless we add 2 to it, and notice we're adding it and then we're subtracting it, so it balances out area-wise. Notice that the right side of this trinomial is plus 2, not minus 2. So when this plus 2, that's what these red ones are here. And so then if you think about what's left over, it's just this rectangle right here, which is 4x and then only 3 more. Or you can think about it as 5x but minus 2, right? And if you take this and you fit it over, it fits perfectly. And on the bottom, it's 1 taken away from 3x. So we have this length of 3x here, but we're just taking away 1 unit here after this line. Which, if we rotate this, 3x minus 1 and 5x minus 2. So everything works out here anyway, as far as area. So I thought that was pretty cool. If you're just learning how to factor trinomials, or you just want to refresh and just want another way to think about it conceptually that might help, this might help. So I'm just going to show you real quick too. Or in order to make this work, I made an Excel macro here. So I made one sub procedure. This is one of them, to actually make the colored shapes. It's kind of difficult sometimes when learning like Visual Basic for applications for like Microsoft, to remember like all the hierarchy of all the objects. But this is what I did. You can also use this like the screen recorder for the actual macro, for the actual procedure, to make like to actually record, which is what I did here, to record what it did. And you can also learn from that, which is kind of cool. And then when you do, you can just kind of change some of it so it suits your needs for like a loop or something when you want to repeat a process. This is the second button down to make the blue rectangle, and then to delete the shapes, I made this one. For this one, I had to really customize this part, especially because I had to not delete the buttons because the buttons will get deleted on this if you don't specify what to not delete out of all the shapes, because these are also technically shapes. Anyway, I hope you liked this video, and I hope it helped you or taught you something.